So in today's module, we're going to finish out Chapter 6. We're going to take a look at finishing out what actually creates line spectra, and then we're going to take a look at the quantum mechanical view of the atom today, where we get the shapes of the orbitals that we use today, where the electrons reside today, and how we think about electrons today compared to how we looked and thought about electrons in Dalton's view or in the view of the early 1900s. We think about it a little bit different with respect to quantum mechanics today and how that explains the behavior that we see today. And so we're going to talk about wave functions, which are basically a probability distribution that create a probability distribution of where an electron resides in space. And that mathematical model, that mathematical shape, is what gives us the shape of the orbitals that we use today. And that's what's depicted over here on the right. Those pictures represent the different orbitals that we're going to be working with and the different shapes of those orbitals. So our first few quick announcements, right? Module 6, both the pre and the post lecture are going to be due Sunday night at midnight. So Sunday, October 18th at midnight. As a reminder, I said this on Tuesday, I'm saying it again, that I will be submitting mid-semester progress reports based on Exam 1, Exam 2, homework, your play, pause, participation as well. And you're going to get one for recitation as well. So up to the, we're halfway through the course at this point. So, everyone give yourself a pat in the back for making it halfway through the course. We've made it so far halfway through, and we've got 5 chapters to go. So you'll be getting those announcements. I'll basically be sending it out based on exams, based on your homework. And I'll let you know, doing a great job in the class, keep it up, or you're showing improvement in the class, or, okay, we've got some work to do to improve our grade. So if I send you one of those flags, please do not take it in a negative way. Please do not take it and just think you need to quit the class and withdraw. No, think of it as this is like I'm trying to start a conversation to figure out what we could do better, what we could do differently for the next 2 exams to get you through the semester. Just a reminder, I'll have the review session my every week, Friday 1 to 3 p.m. on Zoom. I'll have that review session. And then Sunday, I'll have office hours 8 to 9 p.m. So if you need any last minute help on your homework, there's the Friday session 1 to 3, and then the Sunday session 8 to 9 p.m. on Zoom. All right, so today's objectives, we're going to kind of understand, so this is kind of building off of what we talked about earlier in the week, but understand, right, the wave-particle duality of light, understand the relationship between energy levels and light and the energy that's absorbed or released. And so talking about those emission spectra, those excitation spectra, as what do they actually represent? When I see this color being given off, what does that mean for the atom, right? What transition is taking place within the atom, and how does that tell me something about the energy of that transition within the atom, right? The quantized energy levels that I have, right? Specific energy levels, and when I transition between those levels, right, I'm either absorbing or releasing specific wavelengths of light. And then the last thing we're going to look at is how to understand, quantum mechanics and how that was used to expand our understanding of electrons, where electrons reside in space, and how we use quantum mechanics to develop basically our understanding of the shape of an orbital and where exactly an electron resides in that orbital. All right, so one important thing from our last lecture that is definitely important and we need to remember are the 2 main equations that we covered in our last chapter and how we can relate those equations and what they mean. So I can use these 2 equations, right? So speed of light equals my frequency times my wavelength, and energy equals Planck's constant times my frequency. So in a normal calculation, if we were looking for energy and we were given wavelength, right, I'd have to do 2 calculations to take wavelength, given the speed of light, to find frequency, and then plug in frequency to find the energy. But fortunately, because there's a relationship between frequency and energy, there's a relationship between wavelength and frequency, I can combine these 2 equations, and they help give me an understanding about the relationship between frequency and energy and wavelength and energy. And to do that, to combine these 2 equations, all I'm going to do is rearrange that the speed of light equals frequency times wavelength, and I'm going to do that by dividing across by my wavelength. divide across by wavelength, that cancels. I get frequency equals the speed of light over lambda, which is my wavelength. Then I'm going to go over here and see that I have frequency right here, and I know that frequency equals the speed of light over wavelength. And I'm going to plug this in directly in place of my frequency to give me a combined equation now where energy equals Planck's constant times the speed of light divided by my wavelength. And now I can get a direct relationship. I can directly calculate my energy, right, as a product of my wavelength or vice versa using this combined equation. But just to help give us a good idea also of the relationship between wavelength and energy versus frequency and energy, right? Frequency and energy, as frequency increases, right, this is a direct relationship. Energy would increase. If I look at wavelength, on the other hand, right, wavelength is in the denominator. So if my wavelength increases, as this gets larger and larger and larger, when I divide that through, my energy gets smaller and smaller and smaller. So there's an indirect relationship there. So high frequency, high energy. Low frequency means longer wavelength. Longer wavelength means lower energy of light. That's an important relationship to understand as we move across the electromagnetic spectrum. And just to think about that for a minute and take a look at the visible spectrum, for example, right down here at 400 nanometers and just below, we have UV, right? UV light is high energy light. Why is it high energy light? Because it has a short wavelength. Because it has a short wavelength, it has a high frequency, right? Okay, that high frequency means it's going to have a higher energy of light, right? So why are we concerned about UV light and UV light exposure? Because it's higher energy light. Because it's higher energy, now we're worried about, we're on scale of the energy of the chemical bonds in our body, and we don't want to change those because that's going to lead to cancer, right? So as we move to the left side electromagnetic spectrum, we've got shorter wavelength, higher frequency, higher energy. As we move to the right side of the electromagnetic spectrum, I have a longer wavelength, lower frequency, lower energy.